Does anyone have questions on the homework? Nobody. I see one person. Feel free to turn on your cameras if they were off so that I can see you for a more successful class experience. Okay, no questions? How about the graphing homework? Let's see. I'm sorry that your camera broke, Sebastian. That's terrible. It's probably a hard time to get a new one too. All right, let's see. How many of you turned in your graphing homework? Oh, we got 9 people who did the graphing homework. It's better than last time. Excellent. Excellent. Okay. Wonderful. So last time we were talking about finding rational zeros, talking about possible rational zeros. Oh, yes. Anything that you turn in on the homework is always better than nothing, Angel. Okay. Oh, my goodness. I see my family walking to the park. The dog is about to go nuts. They have to go earlier now because it's getting dark. Okay. So let's see. Oh, let me recap. Last time, we talked about using the rational zero theorem, which stated that we could take factors of the constant and divide that by factors of the lead coefficient to get possible rational zeros for our polynomial function. So we generated a list. Now, of these values, that doesn't mean that all 8 of these values are actually going to be zeros of the function. I mean, maybe 1, maybe 2, you just never know. Maybe none of them. Sometimes you'll only have imaginary zeros. So this doesn't cover cases where you have imaginary zeros. But this is saying that if you do have rational zeros, then this is the list from which you would get them. So that's why we have this theorem. Now, also thinking about what we did last time we were given, and you did a bunch of this on your homework, something like, let me find a good one. Let's see. Something like number 6. So you were given an equation, and then you were given one value that was a solution. And in the case of number 6, that value is -3. And then you were asked to find the remaining zeros. So the whole point of what we're going to do today is we're going to combine this idea with our own finding rational zeros from the rational zeros theorem. So we're now going to be looking at polynomial functions. You're going to be asked to generate a list of possible zeros. From that list, you're going to find one that works. And then when you do, you're going to use this process to find the rest of the zeros. So, all right, let's move forward here. And 3.4, now that we've sort of recapped. Properties of roots of polynomial equations. All right, so this is important. I'm going to remind you of it when we get to the next page also, because it's going to apply both places. If a polynomial equation is of degree n, then counting multiple roots separately, the equation has n roots. Now, the whole counting multiple roots separately thing, that has to do with multiplicity. So if you'll remember, we had some situations back in 3.2 when we found zeros, and sometimes we had them with multiplicity 2 or 3. That means that if it's multiplicity 2 or 4, for instance, you're seeing that behavior where the graph will touch the x-axis and turn around. If the multiplicity is 2, that means the 0 shows up twice. If the multiplicity is 3, that means the 0 shows up 3 times. So when we're accounting for these n zeros for our nth degree equation, those could be repeats. So situations where the multiplicity of that 0 was greater than 1. So that's important to note, and I'm going to show you an example where just that thing occurs. Number 2, If a plus bi is a root of the polynomial equation with real coefficients, so b cannot be 0, then the imaginary number a minus b is also a root. Imaginary roots, if they exist, occur in conjugate pairs. So it's probably been a while since you talked about conjugates. Maybe when you were rationalizing some sort of complex numbers back in your previous algebra class. But these conjugates would be something like a plus bi, a minus bi. Sorry, I'm missing some information on the chat here. Which page are we on? Yes, 3.4. You guys are so on top of it. Thank you. Sometimes I get very lost in my my explanations and I lose track of what's going on in the chat. Yeah, we're in 3.4. Yes, yes. Go print that out. Wonderful. Okay. So a plus bi, a minus bi. If one's a root, the other's also going to be a root. That's a given. And you can just take that for granted and use that as often as you need to. The fundamental theorem of algebra. If f of x is a polynomial of degree n, where n is greater than or equal to 1, then the equation f of x equals 0 has at least one complex root. Now, a complex root, sometimes when you hear complex, you think imaginary. That's not the case. If you're thinking about numbers, you have a group of real numbers. So any sort of real number you can think of, 2, the square root of 5, pi, these are all real numbers because they're not imaginary. But then you have a larger spectrum or a larger set of numbers called imaginary numbers, or a different set called imaginary numbers, I should say. But these all fall under complex numbers. So this set out here includes imaginary numbers. So the set of complex numbers includes real numbers and imaginary numbers. So when you see that your equation f of x equals 0 has to have at least one complex root by the fundamental theorem of algebra, that doesn't mean that it has to be an imaginary root. I think that we get confused about that because when you're introduced to imaginary numbers in your algebra class, it's always called complex numbers. And that's the first time you see it. So you think, oh, imaginary means complex. Not the case. Complex numbers include real numbers and imaginary numbers. So that just means that as long as you have a polynomial of degree n where n is greater than or equal to 1, then you have to have at least one complex root. So use that as you will. All right, so now we're going to find a rational zero of the polynomial function, and we're going to use it to find all the zeros of the function. So kind of just like I was saying before, combining these two topics of, once you have a root, finding the other roots, but now in 3.4, being able to find that first root yourself. So when we're doing this, we need to generate a list of possible rational zeros for our function. So looking at your function, make sure that it is in decreasing order first. So x cubed, x squared, x, and then your constant. So that's good. We're looking for the factors of 8 divided by the factors of 3. And we're going to take this and we're going to generate a list of possible rational zeros. We're going to find one that works. I'm going to show you a shortcut for that, but you're still going to have to show your work. And then we're going to solve for the remaining zeros. Now, this is a third-degree polynomial. You're expecting to find 3 roots. So your factors of 8 are 1, 2, 4, and 8. And we can use either positive or negative of any of those values. And for the factors of 3, you just have 1 and 3. Positive or negative for both. Now to generate our list of possible rational zeros, so these would be the numbers we want to test, we're just going to use combinations of these values. So starting, if you would like to just pick a denominator and go with that, 1 over 1, 2 over 1, 4 over 1, 8 over 1, and then you can work with your denominator of 3. So that would be 1/3, 2/3, 4/3, 8/3. And always check and make sure that you didn't end up repeating a value that you had before. In this case, we didn't have anything we could simplify, so that wasn't an issue. Now, officially, you would have to test not just 1, 2, 3, 4, 5, 6, 7, 8 zeros, but you'd actually have to test 16 zeros in order to maybe find the correct one. You know that it's possible that only one of these is a root to your equation. So what we're gonna do is we're gonna take our list, just look at it, give it a gander. And then I'm gonna show you kind of a faster way to do this. Now, normally I would do this on my graphing calculator. However, as you know, I'm having issues right now because I haven't gotten an emulator yet. And with the lighting, I can't get it to show up properly. But you are more than welcome to do this on your graphing calculator. For presentation purposes, I'm going to show you how to do this using something called Desmos, which you may or may not have used before. I hadn't used it in a while, so let me switch over. I'm going to stop presenting just so I can present my screen because I can't present both at the same time. All right, so you should be able to see my screen, yes? My graphing screen. Yes, no one's saying anything. Okay, excellent. All right, now I just went to desmos.com and you can do /calculator or it's like the first option you see when you get on there. You could also use your TI graphing calculator. So what I'm going to do is I'm just going to enter in this function. You don't have to say f of x equals. Actually, I don't even think it'll let you say f of x equals. But I'm going to enter 3x and then use your caret, which is shift 6 to get 3x cubed. My caps lock is on. Minus 17x squared plus 18x plus 8. And then I'm going to graph it. I don't know what this is doing. Okay. You know, I don't think it likes my. Whoa. There we go. Okay. Now I can see my tab, but I can't see you guys. All right, so this is what your graph looks like. You can always play around with the zoom in or the zoom out on this just by using your mouse. You can kind of hover over these and it'll tell you what the roots are. Now, you might be saying to yourself, okay, like we have a 3rd degree polynomial and clearly I see 1, 2, 3 zeros, and all 3 of these, -1/3, +2, and +4 are on my list. Why don't I have, I mean, I might as well just write these answers down. Why do I have to do any work at all? Well, the goal is that you're supposed to know how to use the methods from 3.4. So your job is to use the graph to find one zero that works. And then you're going to take that 0 and use it with synthetic division. So if on your test you give me this list and then you just circle 3 of them and you say, okay, I'm done, I'm not going to give you credit for it. We can all plug a function into our calculator and find the zeros. Your job here is to show me that you know how to use this rational zero theorem and you know how to find zeros of a polynomial function using synthetic division. So you're going to pick one of the zeros. I would suggest not using -1/3 because you don't want to have to use synthetic division with a fraction if you can help it. But I would maybe pick one of the zeros that's really obvious to you, like 2 or 4, and start there. So I'm going to start with 2 just because it's a smaller number than 4. And I'm going to use 2. And I'm going to find my depressed polynomial using synthetic division. Sorry. So now that we've seen the graph, let me switch over here. All right, so we've seen the graph. We know what the zeros are supposed to be. Pick one of them. Doesn't matter which one. I would pick something that's not a fraction. Probably easier to pick something that's positive. You decide. And then you're going to use that process that we used back in 3.3 to find the depressed polynomial. So we're trying to get back down to a quadratic by essentially dividing by x minus 2. So let's go ahead and write the coefficients of the function. 3, negative 17, 18, and 8. Now remember that as long as you've done this correctly, you should get a 0 here for the remainder. If you don't, something went wrong somewhere. Probably it was the graph that you made. So do this first, verify that you get 0 for your remainder, and then find the other 2 zeros. So we pull down the 3. 2 times 3 is 6. And then we're just going through that process of multiplying and adding. And if you've done this correctly, you should end up getting a 0 remainder, which is exactly what we want. Okay, now that you have that, go ahead and write your depressed polynomial. Remember that we started out from the right saying we had a constant, not a constant, a remainder. Remainder, constant, x term, and x squared term. So go ahead and write this as 3x squared minus 11x minus 4 equals 0. All right, now I just did a lot. Does anybody have a question? Okay, so really the only thing new here, what happened to 3x cubed? Oh, so Sebastian, when I performed the division, officially what I did was I took this function and I divided it by x minus 2, because we're always dividing by x minus c, and c is 2 in this case. And when I divided it out, I lost a factor of x. So when I'm working on synthetic division, I always have a remainder here. So when I depress the polynomial, I'm decreasing it by 1 degree. And now my new coefficients will only be for a second degree polynomial. Does that answer your question, Sebastian? Okay, wonderful. Anyone else? Questions? Where does the negative 22 come from? So we multiplied and added. So you bring down the 3. 2 times 3 is 6. Negative 17 plus 6 is negative 11. 2 times negative 11 is negative 22. And then again, we're adding. So add these together, you get negative 4. Multiply, you get negative 8. Add, you get 0. Okay. Does that answer your question? Okay. Wonderful. All right, so now we're just going to solve this equation. You guys go ahead and do that. Figure out what your last 2 zeros are. I'm going to turn up my lights in here. It's getting to be that time. Okay. Now this is one that you could have solved by factoring, or you could solve it using the quadratic equation. I'm going to do it by factoring. If you want to do the quadratic equation, check to make sure that you get the same thing. Multiply a times c to get negative 12. The two numbers that multiply to give you negative 12 and add to give you negative 11 are negative 12 and positive 1. Now rewrite your middle term as 3x squared minus 12x plus x minus 4 equals 0. and then factor by grouping. So you'll have 3x plus 1 equals 0 and x minus 4 equals 0. There's where that negative 1/3 comes from. Now you have x equals 4, which, if you'll remember from the graph that we saw, those were the other two zeros. That's great. It's just a really good way to be able to check your work also. Any questions here? Okay. Wonderful. All right, I redid these a little bit down here because there was a problem I wanted to get in, and then I just felt like, meh, do we really need to do both of these? So I switched number 6 to number 5, and then I put down a new number 6. So take a moment to write down number 5 as 3x cubed minus x squared minus 21x plus 7 equals 0. Okay, I was just thinking, looking at number 5, that we actually could have solved this another way using factor by grouping, but that's okay. We'll do it this way because we need to practice it anyway. Go ahead and graph it. I'm going to go put this into my graphing calculator, if you will. All right, so go to your calculator, switch out your function. So this one will be 3x cubed minus x squared. The really cool thing about this too is you can see how every little thing you enter into the function changes it. Minus 21x plus 7 equals 0. Well, actually, we don't put in the equals 0 part. We just want the function. And you can see where the zeros are. Hover over them. 2.646. What do you think? Is that a decimal we're really familiar with? Probably not. 0.333? Yes. Let's make sure that's in our list of possibles, and then if it is, we'll use that. We'll use the 1/3 value. Let's see, switch back. On the calculator, you know what? That's a really good point, Sebastian. If you're doing this on your calculator, which most of you are, it's very hard to see that 1/3. Is that what you're saying? Yeah, okay. Yeah, we'll do. I'll try to show it to you on the calculator so you can see. Yeah, we should do that. Let's do this first, and then we'll go back to that because it is important. All right, so finding your possible rational zeros, you've got factors of 7 over factors of 3. So you can see that 1/3 is in your list of possibles. So you've got 1, 7, 1/3, and 7/3. Now you could have always checked to see if 7/3 was that decimal, but I would probably stick with the 1/3. And we'll go ahead and work on the synthetic division now. So go ahead and put all of your coefficients in your synthetic division. And be really careful with your fractions. 3 times a third is positive 1. And then we're just going to multiply and add. Now, when you are done with this one, remember we're doing remainder. Gosh, that's the second time I've done that today. Remainder, constant, x squared. Anytime you're depressing it, it's only by 1 degree. So that leaves you with 3x squared minus 21 is equal to 0. And then you can use the square root property to solve. And you end up with x squared equals 7, or x equals plus or minus. Don't forget your plus or minus, otherwise you're going to get done and say, wait a minute, I was expecting 3 zeros and I only got 1. Plus or minus the square root of 7. Now, since we're going to do this anyway, the other day I seriously had 3 TI-84s sitting here. And I almost brought one up today, but I said, no, I've got 3 of them sitting up here. Oh, yeah. Problem, here it is. My husband cleaned out this office the other day. And when my husband cleans, things really disappear and I never know what's going on. But I found the calculator. Okay, so a couple of things here. I'll just have to do the tilt thing and that's not too bad. All right, so the question that Sebastian had was about looking at those decimal values, and we will do that. You might want to also verify that the square root of 7 gives you that decimal that you saw on that Desmos graph, which was 2.646. So that definitely is showing up on the graph. So those are your other 2 zeros. One of them was negative, one of them was positive. So you've got these 2, and then the other one was 1/3. Okay, so when you're doing this on your TI, you're entering your function. Actually, it's much better with this improved lighting conditions. Maybe if I do that, it'll get even better. All right, so let's see. We had 3x cubed minus x squared minus 21x plus 7. And then you will graph it. Make sure I would probably zoom 6 first, just to make sure your zoom looks good. Okay, so now I see what you're saying. So what I would show you at this point, if you're not sure, is you would probably eyeball this and say, if I had to pick one from this list, it's definitely not plus or minus 1. It's definitely not plus or minus 7. 7/3 is 2 1/3, and it doesn't look like that at all. So your guess would be that it was 1/3. There are 2 different ways to try this. Probably the easiest way to do this is to actually have the calculator approximate the 0 for you. If I do this, does it get better? No. Here? This is so crazy. Oh, that might be better. Okay, we'll do that. Go to calculate. So the calculate is your second trace, and it takes you to the calculate menu. Put in number 2 for 0. And what we're going to do is we're going to make the calculator approximate the 0. Now, it's always going to start out by asking you for a left bound. Now, your cursor, sometimes you can't even figure out where it is at first. You're going to look for it. Basically, you just want to make sure you're left of that 0. So somewhere left of that point that we're assuming is 1/3. So I can get a little bit closer to it. It really doesn't matter. You can probably just hit enter and then just go to the right of that 0, just so that we're now underneath the x-axis on the other side. And it's going to ask you for a right bound, and then you're going to hit enter. And then it's going to ask you to guess, and you're going to say yes. And now it gives you 0 is x equals 0.33333333, which you can assume is 1/3. That's one way of doing that. Another thing you could do is you could look in your table. Now, I think some of you, or at least I the other day, was set to ask. But you can always set up your table so that you can put in a particular value and ask your calculator to tell you what the y value is. Because if you just go to your table by itself, well, it's not going to give you x equals 1/3. It's just going to be giving you values that change every one integer. So go to your table set and change your independent variable to ask. And what this is going to do is it's going to allow you to just put in any value for x that you'd like, and it's going to tell you the corresponding y value. So now go back to your table and it'll be blank, and you get to enter the value. So if you think that x equals 1/3 is a 0 and you just want to verify that that decimal is correct, well, then you can enter in 1/3, and it will tell you that when x is 1/3, y is 0. So we can always do it that way. You could even put in the square root of 7. I mean, not that you would have come up with that on your own, but this is a good way to even just show. Well, actually now it looks like a bad way to show it because your calculator can only get so close of an approximation. So sometimes it struggles with these radicals. So this number really does zero out. It just looks like it's something other than 0. But it is not. Alas, it is a 0 of your function. Does anyone have a question about how we found these zeros or how to enter any of this on your calculator? Okay, I guess there's good. Okay. All right. Well, I see that 2 of you seem to be just fine. Everyone else is all right? Okay. Okay. Wonderful. Well, now that I have better lighting, let's put the next one in our calculators. Okay, so this was the one I wanted to do because it's a 4th degree polynomial, and it was the only one that I had. So, well, first things first, let's look at the list of possible rationals, because I know it's so easy just to look at the graph and pick one, but officially that's something that you're going to need to know how to do on your own. Because if you were stranded on a desert island and you didn't have your calculator with you and you needed to know what the zeros were, you would need to be able to come up with that list so you'd know which ones to test. You get my gist. Okay, let's look at the possibles. These are plus or minus 1, plus or minus 13, divided by plus or minus 1. So not too many here to worry about. So we're just looking at plus or minus 1 and plus or minus 13. Now, this is only 4. So if you were like, gosh, by the time I could sit here and put this into my calculator, I might as well just do synthetic division on all 4 of these values and find which one gives me a remainder of 0. Honestly, that might be a faster way to do it. But, you know, up to you. Up to you. If maybe you're starting the synthetic division right now just to try to beat me. Try to get that value first. All right, x to the 4th. Yikes. Where am I? X to the 4th minus 6x cubed plus 22x squared. Ah, see, I always do this. This is one of the problems with having one of these fancier calculators. Now I've got this template. All right. Plus 22x squared minus 30x plus 13. See what I mean? You could have just done all the synthetic division and you would have been almost done by now. And I got to double check my function. Okay, looks good. All right, let's graph it. Interesting. So it looks like we have a 0 at 1. And it looks like its multiplicity is even because at the x-axis, the graph touches and turns at 1. Now, again, you can verify this either by using the 0 function in the calculate menu or going to your table, entering x equals 1, and verifying that y is 0 when x equals 1, which it is. So 1 must be our 0. Now, the graph doesn't give you much of anything that's interesting. You could always zoom it out to see if you're missing something that could be happening. Feel free to zoom out as many times as you want. I don't think it's going to get much more interesting than this, though, unfortunately. No. We could change our window around, but you might as well just do the work and then kind of go backwards from there. All right, so we found that 1 is a 0. So let's go ahead and use 1 with our synthetic division. Using your coefficients 1, -6, 22, -30, and 13. You know, I never used to let my students use their calculator to find a 0. I always just made them test them all until they found the right one. And sometimes you test all of them, none of them have a 0 remainder, and then you realize that you just had one little math error, and you got to go back and do them all over again. So it's a little bit nicer just to be able to look at your graph. 1 times 1 is 1. Add, multiply, add, multiply, add, multiply, add. Okay. Now, remember, we verify that it truly is a 0 if when we use this remainder theorem, we end up getting 0. Remember, this also means that f of 1 is 0, like I showed you last week on Wednesday. All right, so go ahead and find your depressed polynomial. Remember, we're depressing it down by 1 degree. So now we have 1x cubed minus 5x squared plus 17x minus 13 equals 0. So normally when you get down to a depressed polynomial, you are able to either factor this or you can use the quadratic formula. However, in this case, we have a 4-term polynomial that cannot be factored by grouping. And it's not quadratic, so we don't have a formula for this. Well, I think there actually is a formula for this, but it's extremely complicated and you wouldn't learn it anytime soon. So what you can do is, in a normal case, you would go back to your graph and see if there's another 0 that you can pop in that you haven't used yet. In our case, we only had 1 0, though. Did we only have 1 0? Yes, but its multiplicity was probably 2. Because remember, it touched and turned at the x-axis. So because we had this behavior where the graph touched and turned, that tells you that the 0, 1 has an even multiplicity. So I'm going to make a note of that here. The 0, x equals 1, has even multiplicity because the graph touches and turns at x equals 1. Elizabeth, I had missed your comment, but yeah, I agree. You just never know. You just never know when you're going to need to find these zeros in your life. Okay, so because the 0 has an even multiplicity, we know that it's a 0 more than 1 time. Doesn't matter if it's 2 times or 4 times, we just know it's more than once. If you know that that has a multiplicity of 2, you can use this number again. So I can take my depressed polynomial, I'm actually going to squeeze it in here because it fits right underneath what I'm doing. 1, -5, 17, -13. And you can actually depress this down 1 more degree and get it down to a quadratic. So like I said, if you did not have this situation of multiplicity 2, then go back to your function and find another 0 to try out and use it on the depressed polynomial. But in our case, we can depress this down further using the same value. And you'll see that you will indeed get a remainder of 0 when you use this again. Excellent. Now this gets you to a quadratic function. once you have something quadratic, you can go ahead and solve using the quadratic equation. While you guys do that, I'm going to finish up my attendance. You should be getting 2 plus or minus 3i. All right, so using the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all divided by 2a. And then you have 16 minus 52, which is negative 36, which means you have 4 plus or minus 6i over 2. Cancel out a factor of 2, and you have 2 plus or minus 3i. So those are your other two zeros. So you had x equals 1 twice and 2 plus or minus 3i. So if you were trying to recap, we would have x equals 2 plus or minus 3i and x equals 1 twice. So that means you do have 4 roots. Are there any questions on number 6? Okay. Remember also that you cannot see these imaginary roots on the graph. Okay. Oh, yeah. Let's skip number 7. It's basically the same thing that we've just done like 3 times. Okay. All right, so what we're going to do now is use the linear factorization theorem to find polynomials with given zeros. So we're going to work our way backwards now. Instead of you finding zeros given a function, now you're going to be given zeros and you're going to find a function. So if you have this polynomial function, n is greater than or equal to 1, a sub n is not equal to 0, then f of x can be written as a sub n times x minus c sub 1, which is one of your zeros, x minus c sub 2, x minus c sub n as your last factor. So you can write this in factored form. So c sub 1, c sub 2, and c sub n are complex numbers, possibly real, not necessarily distinct. As you saw in the last example, it could be the case that you have x minus 1 times x minus 1. That's what it would have looked like. An nth degree polynomial can be expressed as the product of a non-zero constant and n linear factors, where each linear factor has a leading coefficient of 1. So we're going to work our way backwards here. So as long as you know the degree of the polynomial and you're given a real 0 and an imaginary 0, or even just real zeros, you can figure out what the function is. And in this case, you're given some information about the value of the function. So we're going to set this up using factors, and then we're going to expand it out, solve for the lead coefficient, and get our function. Now, we do need to, and I'm going to remind you of this theorem that you saw, because it's been a while now. You have that I is a 0. You also were given information here that if a plus bi is a root, then a minus bi is also a root. So we're going to use that here. So since we know that I is a root, then I is really the same thing as, I don't know, you can write it as 0 plus I. So if you wanted to write it in the form a plus bi, that's what it would look like. I mean, if you really wanted it to be a plus bi, technically you could say 0 plus 1i. Then you could also say that negative I is also a root. So a plus bi equals I, and a minus bi equals negative I. So if you have I as a 0, then you also have, by definition, negative I. Okay. So we have 3 zeros. We have information about the function that will lead us to the lead coefficient, and we know the degree. So we're going to go ahead and set this up using this formula that you see up here with the factored form. So we have f of x equals. One thing that people are most likely to miss in this problem is they forget to look for that a sub n. Now you can just call it a. It's just whatever your lead coefficient is eventually going to be, but it has to be there because we can't just assume that the lead coefficient is 1. And in this case, it very likely won't be. So start out by f of x equals a. You don't have to worry about a sub n. You could write that if you so desire. And then we're going to set up our factors. Now remember that if we have a 0 of 1, we originally got that from a factor of x minus 1. So if you're thinking about how to work this in reverse, I mean, think about what we did here. If we have a 0 of x equals 4, then we had a factor of x minus 4. So we work our way backwards by taking that opposite sign. So let's see. We have a 0 of 3. So we have a factor of x minus 3. And then we need to think about our complex zeros, x minus I and x plus I. Now, technically, this would just be x minus the 0i and x minus negative I, but x minus negative I is just x plus I. Okay, now the thing that you probably haven't done in a long time is multiplying complex numbers. So let's hold on to everything else that we have right now, and we're going to strategically multiply here. If I were you, I would not multiply x minus 3 by x minus I. Multiply the two complex factors together first. So to FOIL here, you will end up with, and don't forget your parentheses, x squared. And then you have plus ix minus ix. I'm going to write mine. If you don't want to write yours, that's fine. They're additive inverses. And then be careful here with your last terms because you have minus I squared. And now I'm going to remind you that the square root of -1 is I, and I squared is equal to -1, because we're going to have to simplify this. You don't want to have any i's left in your simplified expression. Now I'm just going to rewrite that second factor. So we have x squared, the plus ix and the minus ix go to 0. And then when you have negative I squared, well, if I squared is -1, then you have -1, which is +1. So you're just going to swap that out. Are there any questions so far? Okay, wonderful. All right, so now you can go ahead and multiply your other two binomials. Leave that a out front. So you have x cubed plus x minus 3x squared minus 3. All right, so now we can go ahead and use the fact that f of 2 is equal to 25 because we need to be able to solve for this value of a. Technically, we could have done it back here, but we already expanded it. So let's solve for it here. F of 2 equals, now everywhere you see x, swap it out with 2. You don't have to use parentheses in this case if you don't want to, since we're only talking about evaluating at a positive number. Everywhere you see x, swap it out with 2. And then once we get that value, we'll set it equal to 25. So you have a times 8 plus 2 minus 12 minus 3 equals 25. 10 minus 15 is -5. And then you have a equals -5 when you divide both sides by -5. Now you're not done yet. We're still going to have to put this back into our expression. But does anybody have a question about how we solve for a? Excellent. Once you have a, plug it back in. I'm going to go back to this step in my function where I had f of x equals a times x cubed plus x minus 3x squared minus 3. Where did I get 12? Oh, because I took 2 squared, which is 4, and multiplied it by 3. Don't forget your order of operations. Some of you might have accidentally taken 3 times 2 and then squared it. Be careful. Does that answer your question, Angel? Yes, excellent. Wonderful. All right, so we have, I went too low here. F of x equals -5 times x cubed. Might as well write this in descending order. Minus 3x squared plus x minus 3. And then the last thing you need to do, because you're almost done here, and this is the point at which MyMathLab would tell you that although your answer is equivalent to the correct answer, it's not in the proper form. Expand that out all the way. Your function is -5x cubed plus 15x squared minus 5x plus 15. And if you're feeling spunky, you can always go back through this and find the zeros, and you better figure out that once you have those zeros, they are 3 and plus and minus I. And we're going to do one more of these. Does anyone have a question on this one? Okay, the next one's a little trickier because the complex numbers in the next one are binomials. Find an nth degree polynomial function with real coefficients satisfying the given conditions. Now, in one way, this one's a little easier just because they're telling you that the lead coefficient is 1. If the lead coefficient is 1, then you don't have to go through and solve for A. You know A is going to be 1 in this case. But given the fact that you have a 0 of 3 plus 2i, you need to use that conjugate theorem to come up with the other 0. So that means that 3 minus 2i is also a 0. So let's set this up. It's a third degree polynomial. So we have f of x. You can skip the a in this case since you were told the lead coefficient is 1. You'll know that a is 1. No big deal. But you'll have a 0 of -1. If you want to just go straight to calling it x plus 1, that's fine. I'm going to just go ahead and say x minus -1 just for the notes. You don't have to do that. I just want to make it clear that every single one of these factors is using a negative or minus sign first. The other zeros would be x minus, in parentheses, 3 plus 2i. The last one would be x minus, in parentheses, 3 minus 2i. I see these get messed up so many times. Please be careful about your parentheses here. Make sure you're using them. If you don't use them, you're going to have a lot of sign errors. Does anyone have a question about the way this is set up? The setup is crucial. Okay. All right. Well, let's go through and simplify. What I'm going to do first is I'm just going to simplify these signs. So the first factor will be x plus 1. The second one, I'm going to rewrite this second factor, getting rid of these minus signs. Or I'm sorry, distributing. So I'm not getting rid of them. I'm distributing into the parentheses. So I have x minus 3 minus 2i and x minus 3 plus 2i. And again, I would suggest that you multiply the complex numbers together first and then multiply the binomial in last. Now, this one's a little bit trickier because you're taking a trinomial and multiplying it by a trinomial. So if I were you, I would take the x and I would multiply the x into all 3 terms first. Then I would take the -3 and multiply that in. So that's what I'm going to work on here. X times x is x squared. X times -3 is -3x. And then x times 2i is plus 2ix. And then I'm going to go ahead and work with the -3. I usually do this vertically, but in this case, I'm going to do it horizontally. So -3x. -3 times -3 is +9, and -3 times +2i is -6i. And then work with the -2i. So you'll have minus 2ix plus 6i minus 4i squared. If anything looks fishy, let me know, because there's a lot going on here. Okay. And then don't lose anything. Now, the nice thing is because these are complex conjugates, you're going to have these I terms that are going to cancel out. So 2ix and negative 2ix, those are additive inverses. They're going to go. And you're also going to see that same behavior with the positive 6i and the negative 6i. Those are gone. So let's go through and simplify. And I want you to remember that I squared is equal to -1. So you're really going to take this term and call it -4 times -1. So that's what we're going to simplify in the next step. Does anyone have questions so far? Okay. Leave your x plus 1 alone. Simplify what you can. You have x squared. Oh, I forgot we have, oh no, we don't have x's canceling out. You'll have -6x. And then the only other non-x's that you have are 9. And then you'll have 9 plus 4. Sometimes when students are doing this, they don't bother rewriting it at all. They just, when they see an I squared term, they just think about this as being plus instead of minus, or they just switch the sign on it. So this is really 9 plus 4 to get you to 13. Okay. Now we are almost done. F of x equals, we'll go ahead and multiply x plus 1 into this trinomial. So we have x cubed minus 6x squared plus 13x plus x squared minus 6x plus 13. And then we'll simplify. And that is your function. Are there any questions here? Okay. The last thing to do is Descartes' rule of signs. Now, I don't usually put a whole ton of focus on this, but since I'm going to be spending a little bit of time in class on it, expect to see one question on your exam covering the rule of signs. However, on your homework, if it says to use the rule of signs, I want you to know what it is. So I want you to be able to use it. I'm not going to require you to use this when you are solving equations. So even though you're going to use it on your homework and it's good to practice it, it's kind of something that I'm going to let you use when you want to use it. But I will specifically say use the rule of signs, but when I ask you to solve equations, I'm not going to have you incorporate that in there. Does that make sense? Okay. All right. I can only see one person, so I'm just going to have to take her word for it. Okay. You have this polynomial function with real coefficients. The whole point of Descartes' rule of signs is to give you an idea how many real zeros you're expecting and what their signs would be. So the number of positive real zeros of f is either the same as the number of sign changes of f of x or less than the number of sign changes by a positive even integer. If f has only one variation in sign, then f has exactly one positive real zero. The whole goal is it's just to sort of guide you so that you have a clue of what you're expecting to see. So if you only found, for instance, one real zero and you're like, gosh, there must be more of them, what am I missing? Well, you would know there would only be one real zero if you did the rule of signs. You don't have to do it, but it can be a really helpful tool. So that'll tell you about the number of positive real zeros that you have. In order to find the number of negative real zeros, you're going to check the sign changes for f of negative x. So we're going to be evaluating f of negative x and basically applying the same rule. to find those sign changes. So I'm going to show you how this works. It's pretty straightforward. If I'm looking for the number of positive real zeros of the function, then I'm going to look at f of x and determine how many times the function had a sign change. Now, in order to get from the first term to the next term, we would say that there was one sign change because we went from positive to negative. So that makes 1. And then we went from negative to positive. So that's another 1. But then from positive to positive is not a sign change. So we would say that f of x has 2 sign changes. So there will be either 2 or part B of this rule is it'll be less the number of sign changes by a positive even integer. That means just subtract 2 from it. So if we would have gotten 4 sign changes, we would get 4, 2, or 0. But in this case, we had either 2, subtract from that 2, and you get to 0. So there will be either 2 or 0 positive real zeros. So kind of helpful, but also if you're like, well, 2 or 0, I mean, that's still a lot of open territory. Any questions on this part for this function? Okay. So the next thing would be to determine the number of negative real zeros. So to do that, we're going to find f of negative x. That means everywhere you see x, replace it with negative x. So we'll take negative x to the 7th, and then minus 3 times negative x squared plus negative x plus 7. We're going to simplify that, and then we're going to look at the number of sign changes. Now remember, if your exponent is odd, then your factor here will be negative. If your exponent is even, then it's going to go back to positive. So negative x to the 7th is negative x to the 7th. Multiply that by 5 and you get negative 5x to the 7th. But negative x squared, well, negative x times negative x is just x squared. So you'll just have minus 3x squared still. Nothing changed for that one. So if you remember that rule to just look at the exponent and change it if it's odd, then no big deal. Then you'll have minus x plus 7. And you'll look at the number of sign changes. So from the first term to the second term, you didn't have any sign changes. These were both negative. And then from negative 3x squared to negative x, also both negative. But to get from negative x to positive 7, you have one sign change. So f of x has 1 negative real 0. And now we can't subtract 2 from this because we'd get to a negative value, and we can't have a negative number of negative real zeros. So that's it. We'll just say it has 1 negative real 0. So now in this case, I would say that using the rule of signs would be helpful because you would know already, like if you had 8 values to test and you didn't have your calculator and you were like, gosh, I have to use synthetic division on 8 values. Well, if you did the rule of signs, you would know that f of x has to have 1 negative real 0. Then you could say, oh, no big deal. I won't test the positive values. I'll only test the negative ones because I know there has to be one of them. Whereas you don't know that there are any positive real zeros. There might be 2 of them, but there might be none of them. So it's not so helpful in this case, a little bit more helpful as far as the negative real zeros are concerned. We'll do one more example of this, but does anyone have a question about number 10? Okay. Number 11, same idea. So look at the sign changes for f of x. There's one, there's another one, and there's another one. So we would say that f of x has 3 sign changes. So there will be either 3 or subtract 2 from that, 1, positive real zeros. So there could be 3 of them. There might be 1. So I guess that's kind of helpful because you're at least expecting to see something. It's better than 2 or 0. So now we'll go to negative x, or f of negative x. Go ahead and evaluate the function at negative x. I remember from our exam that some of us really still need to work on evaluating f of negative x. So now's a good time for you to get extra practice. So negative x to the 9th is going to stay negative. So a negative times a negative is a positive. So we'll get positive 6x to the 9th. And then minus x to the 5th. No, negative x squared is just x squared, but there's still a minus in front of it. And then plus 8. We have 1 sign change and then 1 more sign change. So here's another instance where we either have 2 negative real zeros or no negative real zeros. Michael wants to know, how is that x plus 8 and not negative x plus 8? Are you talking about this part, Michael? You can unmute if you want to. I don't know if your mic is not working. I know that sometimes happens.
No, I was having a question because it says negative to the negative x to the 2nd plus 8. So wouldn't negative x be a positive x? Because there's a 1 in front of the
I see
negative.
what you're saying now.
Is
Yeah.
there 1 in front of the x? So it'd be negative 1 times negative x.
But you have to use the order of operations first. So you can't multiply first. You have to apply the exponent of 2. So when you take negative x and square it, you get negative x times negative x, which the negatives now, 2 of them give you a positive. Yeah, so this is positive x squared, and then the negative is still in front of it. Is that clear?
Yeah, thank you.
Okay, good. I'm really glad you asked because I'm sure that someone else was thinking the same thing. So thank you for asking. Okay. All right, so that was the rule of signs. Now, I believe that's the last thing I have in 3-4. So let's just get into the basics of 3-5, and then we'll finish up 3-5 next time. And I have a feeling that 3-5 is going to take up most of the next class period, but we're going to have to evaluate because we're probably going to end up in a situation where we have 20 minutes left. And then I have to decide, are we just going to work on 4-1 or are we going to try to do 3-7? I don't know. I'm going to think about it. We're probably going to want to get a head start on 4-1. It wouldn't be on your test though. Your test will only cover the chapter 3 stuff that we cover. Okay, so Angel, go print out your 3-5 notes. Okay, there's that. Okay, so we have already talked a lot about some of the topics in 3.5, not all of them, and some of them are going to be new to you, like the idea of a horizontal asymptote. A lot of you probably haven't seen that before. Vertical asymptotes you might have talked about. But let's go ahead. We're going to talk about rational functions in 3.5. Now, that being said, you already talked about polynomial functions in 3.2. We're going to talk all about rational functions in 3.5. We're also going to talk about their graphs. So I will have some graphing by hand stuff for you to do from 3.5 to help you prepare for your exam. So you focus on 3.1 quadratic functions, so polynomials of degree 2. 3.2, you talked about polynomial functions. So we were graphing all kinds of polynomial functions, talking about their turning points and all the interesting things that could happen with them. In 3.5, we're really focusing on rational functions. Now, rational functions are written as the quotient of two polynomials, and we'll get to that in the definition here. Yep, there it is. A rational function can be expressed as f of x equals p of x over q of x, where p and q are polynomial functions and q cannot be equal to 0. You're going to find that rational functions have very different properties from polynomial functions. We're not going to be talking a lot about turning points and well, we will talk about end behavior, but we're not going to be talking about all the zeros and the turning points, even though we will focus on x-intercepts. Most of what we talk about with rational functions will have to do with asymptotes. So we're going to really focus on that and talking about the domain, because just the graphs have very different properties. So let's get into this. I already kind of gave you this definition for rational functions. It's the quotient of two polynomial functions. The domain of a rational function is the set of all real numbers, except for the x values that make the denominator 0. Now, this is review. We talked about this in chapter 2. We spent a lot of time talking about how to find the domain of a function. So we're just going to do that again here very quickly at the beginning, since this is review at this point. When you are finding the domain of a rational function, you're going to exclude any values of x that make the denominator 0. Now, number 1 is already factored for you. So as long as it's already factored, all you need to do is say that x plus 5 cannot be equal to 0, and x plus 3 cannot be equal to 0. And then solve, and we'll write it in interval notation. So this means that we can't have x be equal to -5, and we can't have x be equal to -3. And then we'll use our interval notation to write this officially. So we can have any value between -infinity and -5, excluding -5. Any value between -5 and -3. And then after -3, any value in this whole world will work. Remember, you're always going to have one more interval than you have exclusions to your domain. Questions on number 1? Okay. I always feel bad when I get to the end of my smoothie that all this like slurping is annoying, but I just like to get to the last of it. It's so good, and it's so good for me too. Oh, so much good stuff. All right, number 2. This one is not factored for you. You're going to have to factor it. I guess technically you could, if you wanted to, use the square root property. So you could say that this denominator x squared minus 1 can't equal 0. That's fine. That's totally valid. And then you would say x squared cannot be equal to 1. The only thing I would say about using the square root property is make sure that you take the plus or minus when you take the square root on both sides. Because a lot of students see this and they say, oh, well, x can't equal 1. We're done. But then you're missing the fact that x also can't equal -1. So you can do this using the square root property. Or you can do this using factoring. So you could say x squared minus 1 is equal to difference of two squares, x plus 1, x minus 1. which cannot be equal to 0. And from there, you would say x cannot be equal to -1, x cannot be equal to +1. However you want to do that, doesn't matter to me. Some of you will do this, some of you will do that. So to write this in interval notation, same idea as the last one. Just exclude those two values that make the denominator 0. Questions on number 2? Okay, now the next one, it's not really meant to be tricky. If you just want to eyeball this one, that's fine. We don't have a formula for the sum of two squares. Now, you could technically pull this denominator out if you wanted to and say, okay, well, x squared plus 1 can't be equal to 0. And then x squared cannot be equal to -1. Fine. Well, then when you use the square root property, you end up with an imaginary number. So in this case, you don't have any real numbers that you need to exclude from the domain. And then if you're just eyeballing this and you don't have to show me any work, you know that if you take any number and square it, it's going to be positive. Add 1 to it, and it's still going to be positive. So you're never going to be able to find a value of x that will make your denominator 0. And if that's enough for you and you feel like that makes sense, I don't need to show any work, that's fine. In a case like this, I would understand that. Your domain would be all real numbers. Okay. Now, vertical asymptotes are not hard to find, but this is kind of a lot to get into in the last 5 minutes. So I think we'll just focus on this next time. And then maybe next time, if we have extra time, we'll just graph a couple extra rational functions. Okay, so I'm releasing you 5 minutes early tonight, and I have some homework up for you. Actually, it technically won't be available till 7:50. I will probably just add a couple domain problems to it, but it's just a lot of find all the zeros of the function. So you're going to be generating a list of possible zeros, and then you're going to test the zeros to see which one work, or just look in your calculator and pick one. Use synthetic division, verify that you get a remainder of 0, factor or solve your depressed polynomial equation. So that'll be mostly what your homework is all about. A little bit of rule of signs I put on there to give you some practice with that. And what else did we do? That's pretty. Oh yeah, and coming up with those polynomial functions given zeros. So you're going to have that, and then I'll put a couple domain problems on your homework to give you a little bit of a start on 3-5. And that, of course, will be due on Monday. And your test is scheduled for Monday. I'm going to remind you over the weekend, but it'll be the same drill as last time. You know, I was wondering, and I think Simon was one of the people who last time said he had an issue accessing the exam. So maybe you guys can tell me. Last time, and I was on here, and several of you, when we had the test, were on here right at 6 o'clock. And I said, go ahead and go to D2L and check, you know, for your test and do the test there. And several people chatted me and said, where's the test? I don't see it. And I even did like a share my screen, here's where it is kind of thing. And some people said it didn't show up. Okay, so Simon said for some reason it showed all instructions but no PDF of it. Because it wasn't is it in an attachment at the bottom? Because when I do student view, it was in an attachment. Clicking on the wrong link. There wasn't an attachment. Because I mean, it's kind of hard to see. It's at the bottom. It was at the bottom of the. Maybe next time. I mean, I'll put it at the top. It showed everything other than the attachment. Because it's so weird. Because when I did the student view. Oh, so Karen says there were 2 ways to see it. One on the calendar. So did the calendar not have the attachment, Karen?
Yeah, no, it didn't have the attachment. It just said like when it was due, and then you could click on it, and I think the instructions was on it, but there was nothing attached to it, and then you had to like see it on the announcements to click on the link. But I don't know if that was a problem.
Okay, okay. Thank you for clarifying, Simon, because I didn't even think about that because I was just like, well, I'm seeing it. I don't know why it wouldn't be showing up. But I guess that makes sense if you're looking at it through the calendar. Yeah, if so, you actually have to go to like the home page for our class on D2L, and then it's right there in the announcements. And it wasn't a big deal. I just ended up emailing it to the class just in case you couldn't get it. But maybe we'll talk more. Maybe I'll just mention it in my email to remind you of where to look because I didn't want there to be all this stress of like, oh my gosh, it's like 6:08 and I'm still looking for the test. Okay, wonderful. I will try to get that graphing homework graded for you for those 9 of you who submitted it, and then yeah, I'll get you some more graphing homework for Wednesday. Super wonderful things happening in this class. Have a good night, you guys, and I'll see you Wednesday. Bye-bye.